We're going to look at two examples today of how we use the calorimetry equation to calculate the amount of energy gained or lost by a sample that is heating or cooling. And then we're going to look at an example as how we can use the calorimetry equation to calculate the specific heat of a particular sample if we know the temperature change and the mass of the sample. These examples correspond to the worked examples in 9.1 and 9.2 in the OpenStax textbook. And we're going to walk you through them. I'll show you step by step how we apply the logic to define system and surroundings, how we use the calorimetry equation to calculate what we need. So in the first example, we're told that a flask containing 8.2 times 10 to the second grams of water is heated, and the temperature of that water increases from 21 degrees Celsius to 85 degrees Celsius. We want to know how much heat did the water absorb. Now, the first thing to notice is that our mass of water is given to us in scientific notation. So you need to be fluent in your scientific notation to convert this to standard notation if you'd prefer to think in standard notation. So 8 times 10 to the second grams of water corresponds to 800 grams of water being heated. The second thing to notice is that the temperature of the water increases from 21 degrees Celsius to 85 degrees Celsius. And we're only interested in how much heat did the water absorb when it went from this temperature to that temperature. So what we have is we have the mass of a sample, and we know what the sample is, and we know how much the temperature changed, and we're asked how much heat did the water absorb. So notice absorbing heat is going to be a positive Q by convention. The positive Q means the heat is going into the system. All right, so because we have the mass of the sample and we know the temperature change, we know that this is a situation where we can use the calorimetry equation, Q equals mc delta T, to determine the heat absorbed Q by the sample of water. So because we know the mass of the sample and we know the temperature changed, and we're looking for the heat absorbed, we know that we should use the equation Q equals mc delta T to figure out Q, the amount of heat absorbed. We know the mass of the sample, so we could plug 800 grams of water in for M. We can find the temperature change. The initial temperature is 21 degrees Celsius, and the final temperature is 85 degrees Celsius. So 85 minus 21 will give us our temperature change. The only thing we need to know is the specific heat of the water, lowercase c, which we can find in a table. Looking up in the table of specific heats, we see that the specific heat of water is, as we said before, 4.18 joules per gram degree Celsius. And just like most equations that will deal with this term, make sure you're watching your units closely here. If you do a Google search, you may also find the specific heat of water given in calories rather than joules. By default, when we're calculating an amount of energy transferred in this class, unless we say specifically that we're looking for it in calories, we're looking for the amount of energy transferred in joules. So you want to use the specific heat that has units of joules per gram degrees Celsius. The idea is that the grams and the degrees Celsius in the denominator will cancel with the grams in the mass and the degrees Celsius in the temperature change. Okay, so having all these values, in this case, we just need to plug them into the relevant equation to find our temperature change Q. Q is equal to 800 grams, that's the mass of the water, times the specific heat of the water, 4.18 joules per gram degree Celsius, times the difference in the final and initial temperatures. So we have 800 times 4.18 times the difference of 85 and 21. Crunching those numbers, we get that the overall energy change, the overall amount of heat absorbed by the water, is 214,016 joules. And considering our significant figures, we have two significant figures in the mass, we have two significant figures in the temperature, so we're only entitled to report the amount of heat absorbed to two significant figures. Our final amount of heat absorbed by the water should be expressed as a positive because the heat was going into the water, 210,000 joules or 210 kilojoules. And so that's the basic use of the calorimetry equation. Whenever we're dealing with a situation where we have a sample of a known mass that's absorbing a specific amount of heat or undergoes a temperature change from here to here, that's your signal that you should use the calorimetry equation, Q equals mc delta T to solve the problem. Come back in a minute, we're going to look at another application of the calorimetry equation where we rearrange and solve for C to determine the specific heat of the sample.